Hi everyone, welcome back to the class. So in this week, we are still in chapter 4, the finite state machine FSM design. In the previous lecture, we have learned the FSM already. You have been introduced to the finite state machine. We have learned the more type finite state machine. You have learned the mealy type finite state machine. And today we will try to do this ESM and the last one FSM D. Um, so for the finite state machine, you should know that this is the general structure of the finite state machine, or the block diagram, or we call it the functional block diagram of the finite state machine, where for more types finite state machine, we don't have this wire or line from the input to the output circuit, right? So for more, when we don't have this line, we can see that the output is only depend on the state of the finite state machine. The output Z is only depend on the present state of the finite state machine. And but for mealy FSM, when we have the signal here, the wire that connected from the input to the output logic here, the Z here is not only depend on the present state of the finite state machine, but also will depend on the input, meaning that the output Z is immediately available when the input change here. All right. So this means that the output for mealy state machine will available faster as compared to the more state machine for one clock cycle actually, right? So last week we have looked at this example where we have the state diagram and we have the state table, all right, and we have the state assigned table. We derive the Boolean equation, and after that we get the or produce this circuit, yeah, and we also learn how to code, yeah, using behavioral modeling, where we don't need this actually, we don't need this process where you need to uh, deriving the circuit before you can get the circuit like this. All right, with Verilog, we only need this structure. All right, and we describe what is inside the next state logic or combinational circuit here, and the output logic combinational circuit here using behavioral modeling. All right, so you can refer back to my previous video how to write the code for this, and also we need to have this, we need to refer this because the behavior of this or the output of this and this will depend on this, right? And this is more type for FSM, and for mealy type we have this, yeah, and we also learned that for mealy we have less complex circuit as compared to more, because as we can see here, the state diagram, the number of state is less as compared to the more, right? Yeah. So today we will continue with this, the serial adder, all right, where we have this is the block diagram of the serial adder, and just like we discussed last week, where when we want to add numbers, all right, we can do that in parallel, all right, and we did design the parallel adder in chapter 2 already. But sometimes when we want a low cost circuit where we only need the uh, the smallest circuit as possible, and the speed, we can compromise the speed, so we can have what we call the serial adder, where we add only bit by bit, yeah, and get the result here. All right, so for example, if we have 4-bit serial adder, so we will use the shift register here and here for the first input and the second input, and we shift the LSB, the least significant bit, here to this wire, and this one to this wire, go to the adder FSM add, and we get the result here and put in the sum register here to the MSB of this register, and shift to the left, shift to the right, and here we shift again 4 times to get the result here. So we can do that using what we call the serial adder, and the structure should be something like this. And this is the state diagram to represent this adder ASM, and the discussion, the explanation for this is given in the previous video, so you can always refer to that video for the explanation how do we get these finite state diagram, the state diagram like this, to represent the operation inside this adder. So today we will write the code for this. All right, and of course, to write the code we need to have the uh, quarters 2 open, where you need to create the new project here. All right, so we create the new project here, and I have this already. Maybe I have a new one here, maybe one, and the name is Billy1, and let's use the default one, and create the Verilog files and module, and of course the name, clock, the reset, and this one you need to have. To write the code for our serial adder, the serial adder, so we need to have the block diagram and also the state diagram. So this is our code. So the name is FSM adder Billy, and of course when we have the register and we have the flip-flop, we need the clock and also the reset. And what else that we need? You need the register, because this is the shift load register, where you need to load data from this A. So you need to have the load signal actually. All right, so let's name this signal as the signal here is LDA, or load A, and you need to load the data to B also. The name is LDB, All right, and yeah, so we have another signal. The name is LDA, and also we have LDB. What else? We have the input to this register, which is A, all right, and we have the input to this register, which is B, okay, and we have the for this register should be done. We have clock, we have reset, and this is the input to the load signal, and we have input to the register A and B. And for this register, you will have the output sum, yeah, sum, and the output from this register also you need to have. Let's name this as rack A, so that we can see later, all right, in simulation what is inside this register. So just name this as rack A and rack B for this one, and we should, right. So now we have input. So for 1 bit input we have this, right, all are 1 bit, and we have let's say our adder is 4-bit adder, so, and should be A and B, right, and we have this is output sum, and this is uh, a variable in the always block, right, because we will describe the register using behavioral modeling. So it should be in rack data type and output also, right, yeah. uh, the size is 4 bit, okay. We have rack A and also rack B and sum, right. uh, and for the FSM, finite state machine, all right. So this is one box, but what is inside is something like this, yeah. Okay, so when we look at the FSM, uh, so this one, in order to design the circuit for this, so we need to look at the general form of the FSM. So you need to have the state register, remember, and you need the, okay, so right, so you have this is actually S, right, and this is your flip-flops D and Q. So you have how many flip-flops in this case? How many? How many state you have? You have 2 state, so you need only 1 flip-flops, right? So it should be 1 bit. Okay, and of course here you have A and B, all right. So this will be the next state logic. This is state register, and this should be the output logic. Okay, and of course you need to have, remember, the feedback from here to here. And also, because this is melee, you need to have this. Okay, right? So this is this circuit in here. Right? You have AB drive the next state logic, and this next state logic drive the state register, and this state registers drive the output logic. And also you need to have this feedback, and A and B also drive the output logic. Yeah? So this is a MIDI FSM. All right, so we want to do this. Yeah? And now let's name this signal as next state, and this signal as state. All right, this is present state. In the previous example, we named this as small y and this one as capital Y. But in this case, we name it this as next state, and this one is state. Right? Okay. So here we need to have this signal. All right, and it should be declared as rect. Yeah, and it's 1 bit. Next state, and another one is state. Okay, so now we have this signal already. Now we need to have this A and B. So A and B can be declared as wire A and B, and we have this one we will declare as rack. All right, rack, because we will assign the value to as using behavioral modeling, because this is flip-flops. That's why the data type is rack. All right, and we need to have the state name. Okay, so we have G and H. Okay, this one, or okay, G and H. So and this is 1 bit, so we can use parameter. Okay, 1 bit, G equal to number 0, and this is 1 bit, and we have H number 1 bit also, number 1. Okay, so now maybe we can describe signal A and B first. All right, so what is signal A and B? Actually, this signal A and B is connected to this. So if we look at this, right, this signal A and B is connected to this register, and when we draw this register, it will be something like this. Okay, and you have 8-bit, right? 8-bit, and this is actually Q, right? The name is we name it as rack. This one is rack A, right? Rack A. So this is bit rack A0. This one is rack A1. This is number 2, number 3, 4, 5, 6, 7 actually. Right. So this rack A0 is connected to this signal A. So means that A and rack A0 is the same signal. All right. So in Verilog, we can just use assign keyword, right? Assign A equal to actually rack A0, and for B is rack B0, right? So this will define this A and B, right? Now we have this signal already. We want to describe register rack A here. Okay. So how to do that? Huh? So we name as this one is rack A, right? So we can use, yes, how to define the register. Very easy. Yeah. For example, our register is positive age triggered. Push age clock, and also positive or active high reset. Okay, so if reset equal to 1, so what we should do, rack A should be equal to 0, right? Okay, so when we reset, this register should be equal to 0, means that the content of the register must be equal to 0. Okay, but if not reset, if reset is not active, so this will be where is it? We have the load A signal, right? LDA, remember? This we have the LDA, and this one we have the LDB. Okay, so if not reset, we will look at this signal. If this signal is 1, means that we load A into the register. But if this signal is equal to 0, means that we do the shift. We shift, right? Remember in the previous lecture, we learned how to design a shift load register, right? Where the function of shift or load will depend on this signal. If this signal is equal to 1, we load data A into the register. But if the value here or signal here equal to 0, we shift the data inside the register from the left to the right. So in this case, we can see that, or we can say that if LDA equal to 1, what we do is we load the data into this register, and of course the data is A, all right? In this case is A. So we load into the register now, right? And if here should be else, right? Else if, because we have if already here, so we should have else if, and if LDA equal to 0, right, means that else we need to do the shift. So how to do the shift? So there are many ways in Verilog, but we have the shift operator, remember, which is this symbol means that this is shift right. If we want to shift left, we use this. All right. So so if LDA equal to 0, what we do is rect A should be, all right, rect A shift to the right one time, 1 bit. If you want to shift 2 bit, you just change this to 2. All right. So in this case, we want to shift 1 bit to the right. So done. So this will be this register. All right. And the signal A here is the output from this register bit number 0. All right, which is this one. This one is A. Okay, here. Right. And what about B? So B should be the same register. All right, same register. The only difference is that the input is different and the name also different. So you can just use this one and have this, and of course we change this to B. Okay, and the clock and the reset is the same signal, so should be no problem. And of course the name here should be B, and the name here should be load B, and this is B, and this should be B, and should be B, and this one should be B, and you get the register B here. All right, should be straightforward. Okay, now we want to create this one, this register. This register is only the chief register. We don't have load. You see, we not loading any value into this register. We just chief from F to the most significant bit MSB here, and only have the output, and we're not shifting any value out of this register. We just shift from the MSB into the register, and the output is read in parallel here. So yes, a little bit different. So we have some again, the clock and the reset is the same signal, so we can use this one. Also, if reset, all right, the output should be equal to 0, but else we want to do the shift. If yeah, if not reset, we do the shift. So how to do the shift? So we can write like this: sum number 3, the MSB is replaced by S, right? Is assigned to S, yeah. And the bit number 2 is assigned to bit number 3. All right, means that we shift from here, we go to here, from here we go to here. All right, And again, we will have number 2 will go to number 1, and the last one will be number 1 will go to number 0. Okay, and again, when we have this many statement, so we should have begin, isn't it? Right. So we have any statement here, and if we have begin, we should have end here. All right, done. So this will be the this one will represent this. All right, this. Now we want to create this. All right. So to create this, we need to have the state diagram, of course, this one. All right, we need to have this. Okay, so we need to create the state register first. The state register. How to create the state register? So again, this, the state register, this one, right? So we can name this as state register. All right, and this we use the same clock signal, so we can use this also. All right, use the same, and if reset equal to 1, what should we do? If reset is activated, so we should be at state G, or 0, state 0, or state G in our case, right? So when reset equal to 0, we should have, or we should stay in this state, G, reset, you see? So, and here G, right, is equal to 0. Okay, so we can say that if reset, we should be at uh, if reset, the output of this, the state, this signal, we call it state, right? Remember, state, the state, which is this one, right? So state should be equal to G, right? And if not reset, the state should be equal to this one, right? Next state, this one, and we name it as next state, this one, and we have this next state, done. So this is our flip-flops, all right, our flip-flop. Now we want to describe this. What is next state logic? What is output logic? Based on what? Based on the state diagram. All right. So we call it next state, and output. We can combine this together. Okay. And we will describe using behavioral modeling. And of course, you need to always block. And we need to list the sensitivity list. Right, so what are the sensitivity lists? What should be inside the sensitivity list? Should be A, B, and also this state. All right, because these three signals are the input to this logic and also the input to this logic. That's why we have A, we have B, we have state. Yeah. Okay, that's it. And now we want to create our uh, this logic and also this logic based on the state. Yeah, so we can say that case state. All right. So if state is at G, all right, or 0 in our case, yeah. So we need to look at, yeah, in order to create this output, next state output, and also the S output, we need to look at A and B, right? A and B. Okay, so if we look at this, okay, so there are many possibilities of A and B. So A and B can be 0, 0, A and B can be 0, 1, A and B can be 1, 0, and A and B also can be 1, 1, and the output is depend on the value of A and B. So because we have many possibilities of A and B, we can use if else, or the best way is to use case statement. Again, case and because A and B are different signals, so you need to combine it using concatenation statement here. So A and B, here you combine A and B, all right? So you can have case if A and B now is 2-bit, A and B is 0, 0, means that this, yeah, this case 0, 0, 0, okay? So if 0, 0, we have two two output, right, bit to be considered, which is the next state and also the S. So if 0, 0, so the next state will be, equal to, if 0, 0, next state will be G, right? Will be stay the same, will be G. And S should be equal to, what is S? Should be equal to 0. And for this, done. All right, for 0, 0. What about 0, 1? So actually we can copy this, change this to 0, 1. All right. And also next state is G, and again S should be equal to 1. It's the same here, 1, right? And when 1, 0, we can have 1, 0 here, right? And the output is the same. Next state should be equal to G, and S should be equal to 1, right? But when we have AB equal to 1, 1, all right, the next state now is not equal to G. So the next state now is equal to H. All right, 1, 1, C, 1, 1, the next state should be equal to H. And the output S should be equal to 0. And that, all right, so this will represent state G. And we have here case, so we can say in case here, all right. And we have state H here, so it should be similar to this, and the difference is only the value of this G here and here. So maybe we can copy this and just change the value in that here. For example, if we are in H, if 0, 0, so what we should do is that this should be if 0 0, yes, should be G, and the output should be 1. Based on this, M is 0 1 1 0 0 1 1 0 and 1 1, we should in H actually, and the output for 0 0 should 0 1 should be 0. For 1 0, we should be still in H, and the output as should be 0. And for 1 1, we should stay in the H, and the output should be 1, like this. All right, done? Yes. This will represent this, and this will represent this. And I think done for this part, yeah, the next state logic and the output logic. Done. And if done, so we should end our module here. All right. So this will create this one for you, and the behavior is exactly should be like this. All right, and we want to see later in the simulation when we have the input A equal to 1, for example, B equal to 2, so the output sum it should be equal to 1 plus 2 should be equal to 3. All right, and we will see that the shifting process, right? And the answer, the output, the result here is not immediately available, but we need at least 4 clock cycle, all right, to shift the data bit by bit and add and to have the result here. All right, we will see in the simulation. Now let's save this and try to synthesize. We have error. State is not declared. Okay, maybe I use this different name. The state here is, yes, I use a small letter for S, and remember Verilog is case sensitive, yeah. So if you use small letter, so you need to be consistent, right? I think that's it. Okay, so there is no error and only one warning, and of course the warning is about the license that we used, so should be no problem for the design. So now we want to create the test bench for this, yeah. So you can go to this, yeah, right? And now let's create the test bench together. We have this and time scale, time scale. Let's have 1 nanometer time scale and 1 nanometer precision, right? And the module name is FSM. And maybe attachment quite long, it should be no problem. All right, and the input to the testbed should be A, B, clock, and reset. Yeah, so and remember the input to the testbed must be declared as rack. Yeah, so we have clock, we have reset, we have the LDA and LDB, and also we have this, yeah, A and B, so we can use this actually. And what about the output? The output is this sum, and also we want to see what is inside A and B. So and must be declared as wire in test bench. So this should be the output of the test bench. Done. And we need to instantiate our design here. All right. So to instantiate, so this is the design that we want to instantiate. So just copy this. The name must be this one, and this one you can name anything. Maybe you can name testbed, or name M0, or name S0, or name whatever you want. All right, the port list. Let's use the same port list as this one. So should be no problem when we use the same port list name. Okay, and we want to monitor we want to have time, and we want to look at this, and also this, and also this. All right, and all should be in binary. And this should be mapped to the, the signal. So we have this, and we can have the clock signal. We start at 0. All right, and we create the clock signal. We can use always or forever also can, and every 10 seconds we toggle the clock. Right, so this will create the clock signal. All right, and the period is 20 nanosecond. All right, because we toggle the clock signal at every 10 nanosecond. All right, now we want to give the stimulus to our design. Okay, so let's, for example, at time 0, we reset our circuit first, and the other signal is set to 0. B also equal to 0 at this time 0 second. All right, and at 30 nanosecond we set inactivate the reset, make the reset inactive or make it low. All right, and another 10 nanosecond. Now we have the input A equal to 3 and B equal to 4. Yeah, and another 20 nanosecond, we try to load the signal into the register rack A and rack B. So we set LD A equal to 1, LD B equal to 1. Yeah, and the next 20 nanosecond, we need to deactivate this signal, right? Make it 0 so that we can shift A and B in the register. All right, and we another 20 nanosecond. Maybe we have A equal to 0. All right, B equal to 0, and let's another 100 nanosecond. We stop the simulation. All right, and and module here. Okay, so this is our simulate attachment. Okay, and number 3, A is 3, B is 4, so we expect that the output should be 7, right, when we add. And let's see, so the name for this one is this one. Need to save using this name. Just save, and let's check for syntax error. All right, so no error, should be good. And now we want to simulate our circuit, so need to do a little bit setting. Format output, better to change to an Verilog HDL attachment. Create a new one. The name should be the same as our attachment file. Here we need to add the file. In this case, this one. Click OK. OK. We need to add here. Click OK. OK and OK. All right. So now we can RTL simulation. Okay. And let's wait for the model sim. Right. Okay, so we have this, and we can zoom it to and let's see what is our okay, so this is A, this is B, this is the input, no, this is the content of register A, or the output from the register A. This is output from register B, and this is the output, actually the sum. All right, so let's look at this. This is based on what we have in our attachment, the stimulus that we set. So here we can see that at 40 nanosecond, based on this, right? At 40 nanosecond, we set A to 3, B to 4, A to 3, B to 4, 40 nanosecond exactly. And here we load, we load the data, A and B, into register A and register B. We can see that at the positive clock edge here, all right, because our register is positive edge triggered. So we can see that at positive here the data is loaded into the register here. We can see that 3 is now in register A and 4 is now in register B. All right. And when we deactivate the load signal, now the shifting process begin. All right. At the next clock edge here, positive clock edge, we can see that this is shifted, right? A from 0011 is shifted to the right. From 0011 we have 0001 now. All right, the 1 is shifted out, and here also the same. We can see that this one is shifted 0010, from 0100 shift to the right, one bit. Okay, so number 0 is shifted out and go to the adder, add, and we will have the output at the sum. All right, 1 plus 0, we have s equal to 1. That's why we have 100 at the sum, the output here. And this is not the output yet, the output that we want yet, because only one bit, the least significant bit are added. All right, so we need to shift again. So this one is the shift. All right, see, we shift again and add, we have this, and shift again 3 times, shift 3 times. This is 1 time, second time 3 times, and we have this, and the fourth time, the shift number 4, we have the result here. All right, this is 7. Okay, we can see that 0111 is 7. All right, so this is the output after 4 clock cycle of shift 4 times. 1 2 3 4, we get the result. Right, so this indicate that our design is correct, based on the output here. So when you change the input to maybe other number, right, other combination. So let's see if we can have this, for example, from 5 plus 4, we should have 9, right, the output. So save and try to run the simulation. Let's see. Okay, so we have this, and after 4 clock cycle, 1 2 3 4, and we have the output is 9 here. All right, so we have the output here, using uh, this is our design, and exactly based on what we have here, this. All right, so any question for this design example? Are you still there? uh, okay, all right, so any question? No question. So if you want to do this again, so you can always refer back to the video, right, in YouTube. And if you have any question, you can ask. So we will have a short break, and we come back and try to have another example where we have, or we want to design this serial adder using now more FSM. This one is milli FSM. So how, if you want to design using more FSM, how to create the state diagram and the code for more FSM.